In this video, you'll learn about how you can apply the physics principles you've learned in class to the design of your egg drop project. In designing the protective package, there are three things you're going to have to keep in mind. The first, of course, is that you've got to protect the egg from breaking. Also, the rules state that the mass of the package can be no more than 100 grams. Finally, you should design your package so that it gets down to the ground as quickly as possible. So you want to try to minimize air resistance in your design. In other words, no parachutes or helicopter rotors. The most critical part of your design will be your crush or crumple zone. You've learned that the purpose of the crush zone is to lengthen the time of impact as much as possible, thereby reducing the force of impact on the package. Another way of saying this is that you want the acceleration to be as small as possible. Your experiment showed that you would like your crush zone to act like the front of a car and crumple or break on impact. Ideally, the impact surface will be relatively flexible and breakable and then get stronger as you move towards the inside of the package. If you decide to go with a symmetrical design, you won't have to think too much about aerodynamics, but you'll have to make sure that the entire project is covered with a crumple zone. An asymmetric design will require you to make sure that the package falls on the crush zone. An important question is where you're going to place the egg. In a symmetric design, obviously it'll have to go in the middle. For the asymmetric design, it's not so obvious. At first you might think that it's best to put it towards the top in order to protect the egg the best. However, it turns out that that won't work. Remember that the crush zone has to hit the ground first, and air resistance will be a factor. Your project could rotate during the fall and land on its top or side. In those cases, the egg is likely to break. The way that the package falls is mainly determined by aerodynamics and the mass distribution of the package. The position of the egg has a major effect on the mass distribution by helping to determine the location of the center of mass. The center of mass of an object is determined by the mass distribution. Here's a semi-technical definition of the center of mass, but for our purposes we can think of it as the average position of the mass of the object. Its position is important because if the package does rotate during flight, the center of mass will serve as its axis of rotation. The picture at the bottom shows how a rotating hammer's center of mass will follow the same parabolic path that a ball would if it was thrown. The picture at the left shows how the position of the center of mass is closest to the heaviest part of the hammer. It's also the balance point of the hammer. It can be found by balancing the hammer on your finger. You'll need to find the center of mass of your package in the same way. Be sure to put an egg or a similar object in the package before you try to balance it. The mass of the egg will be around 60 grams. Therefore, when it's in the package, it will comprise over a third of the mass of the package. That means that the center of mass is likely to be close to the egg. All else being equal, if the egg was at the center of the package, that's where the center of mass would be. But if the egg were lower in the package, that would move the center of mass closer to the bottom. As the package falls, air resistance will cause it to rotate about its center of mass. We call those forces torques. We symbolize them by the Greek letter tau. Let's imagine that the package is falling horizontally. Air resistance applies force to the bottom edge evenly, but that doesn't mean that the package won't rotate. The air resistance being applied to the left of the center of mass would tend to make the package rotate clockwise. We call that a clockwise torque. The air resistance being applied to the right side of the center of mass would cause the package to want to rotate counterclockwise. We call that a counterclockwise torque. The counterclockwise torque is larger here not only because there's more surface area on the right side, but also that force is being applied farther from the center of mass. We call the distance between the center of mass and the applied force the lever arm. There's an imbalance between the two torques. We symbolize it this way. The key point is that the side that receives the most torque will determine which way the package rotates, in this case counterclockwise. See the bottom of the slide for a summary of the situation. If the package over-rotates, the same effect will occur on the other side of the package, bringing it back to the upright position. Since any deviation from the vertical results in a torque that tends to bring the package back to vertical, we can say that the torque applies a restoring force to the package. This is what causes the flight to be stable. So where should you put the egg? Well, if you want it to fly the way you just saw, you're going to have to get the center mass as low as possible, and that means putting the egg as low as you safely can. At the very least, the center of mass should be well below the geometric center. If you want to increase the distance between the geometric center and the center of mass, my advice is to build tall and light. This way, you'll have an increased surface area above the center of mass, as well as increasing the lever arm. Although the center of mass is also going to be raised, if you build with light materials, hopefully the geometric center will go up even farther. But increasing the distance between the center of mass and the geometric center is only a rule of thumb. For example, building a very wide base might provide unwanted torque. Besides building a tower, you could also add some structure like fins that will help stabilize the flight even more. A sleek profile should help cut down on air resistance and help the package get down faster. You'll want to minimize bouncing, since the higher it bounces, the more force must have been applied to the package. Also, you'll have to account for secondary collisions. Finally, be sure to watch several videos from past years so you can see what kinds of things worked and what didn't. And good luck.